Hello world, this is Craig. Let's finish up this series on the 8008 assembly by looking at the last of the pseudo opcodes or the assembler directives. For the most part, we'll look at them after it's been assembled, but this is our Hello World program. I've added a bunch of pseudo opcodes in here, and we'll look at those afterwards in the listing version, but I wanted to show you one of them, which is the include directive. Here's the include directive, and I have a file that's in the same folder that's called ASCII definitions, and this is a way that you can just simply make your code more readable, more convenient, a little smaller, tighter packaging, is by taking things that you aren't really a part of the code, they're just tables or they're just values like ASCII values, and put them in a different file and then use the include statement. When this is assembled, it will just splice in that file into this place. Now, the file ASCII definitions, it could have an include in it, and so on down the line. And I think you can have a total of 7 or so files open at the same time, but that depends on the assembler. The rest of these we will go ahead and assemble and then look at the list file. This is our regular code. The first thing we're going to look at are the data bytes, data words, and data storage. Data byte, as I mentioned earlier, it allows you to take a byte of data and simply splice it into the code. You can see here we have a label called data bytes, the assembler directive DB, and then we have a series of values that are comma separated, and they can be in whatever form, but it just puts it into the code. So the program counter just increments once for each of those values, and those values are put into memory. We can also use data bytes for ASCII strings or text strings. So here's an example where we have our hello world in quotes. We have a pair of commas that don't have anything between them. And when it sees that, it will insert a 0 as that data byte. If you see a 0 mysteriously crop up, it might be because you have 2 commas in a row. And if you didn't have a comma, if you ended this with a comma, or if you didn't have a comma between 2 values, it'll throw up an error for that. The next is the data word, which for this machine is 2 bytes. And so we can put in we have a double byte, 010, 122 in octal. But you can see that this assembler, and this is the A08 on Herb Johnson's website, it interprets that as straight octal and not split octal. So you can see the value that it gives us, instead of 010122, it gives us 020122. So if you are thinking a value is going to be split octal and it turns out that something's not working right, that's a good place to look. Maybe you put it in as straight octal and the assembler interpreted it as such. If you want it to be interpreted as split octal, you need to put in the pound sign or the hashtag in the next example, which is 010 hashtag 122, and you can see that that interpreted that properly as split octal as we intended. And the next example is an address. We've put in as a data word, and it interprets that as we expected. And again, addresses go in as little endian. Next is the data storage. Now, the difference between the data byte, data word, and data storage is that data byte and data word put a value in memory. And so we know what that is. We can come back and we can use that. And the intent is that we're putting a value in memory. If we don't really care what that value is, but we just want to create a blank buffer area that we don't want other code to go in, then we use the DS, which is the data storage. In this example, we're saying, give us 20 values, 20 places in decimal for a scratch pad in RAM. We can see the program counter goes from 010 to 70, and the next time the program counter is used is up here at 010111. So it has just given us a big buffer of program counter here of memory that isn't used. Let's look at labels and names. They're both usually called labels, but actually they're different. Labels end with a colon and names do not. Labels are assigned the value of the program counter at that point for later reference, so we can reference that portion of memory, where names are assigned the value using a equals or a set. So these are some examples of names. There's value names, which equals 123. It's just going to assign that value to the term value name, and we can use the term value name elsewhere in our code, and wherever we do that, it's going to put in the value 1, 2, 3. The next one is called bad name with a colon, because strictly speaking, this should not have a colon after it because it has the opcode EQU to equal something. But this assembler is pretty lax. It should freak out, but it just goes ahead and assigns that. But in strict Intel assembler, this won't work. So it'd be a bad habit to put colons after your names. And in fact, it just completely ignores the colon. It doesn't require that if you're going to use that later that it has the colon. It just drops the colon. It treats it as white space, actually. Next is the new name, which equals hij as a character string. And this isn't going to do what you expected. If you were thinking that this new name was going to use the value hij, it doesn't do that. It only uses the first 2 characters. And so you can see on the left-hand side, it has assigned that 110 and 111, which is just hi. Okay, now let's look at labels. Labels are going to assign the program counter to that value so you can reference that place. Not the value, but that place. Program counter label, put it in as a data byte in this case, and just assigns that value. So we can see over here the program counter is 010314, and it's stuffed into that memory location of 123. Bad label, just as before, the assembler is very lax with the colons after labels and names. So while it should throw this up as an error because it does not have a colon after the label, it's fine with that. And so it just took the program counter 010315 and it put in that same value 123. If we want to put a double quote into a string, we can use single quotes for our string. So when we have a string that we're putting in, data byte or data word or something, we have to match single quotes with single quotes and double quotes with double quotes, but if we want to use one or the other, then we need to use the opposite for the outside quote. So, for example, here I have length is 12 inches, and to get the inch or the double quote, I used single quotes to contain my character string. In the next one, where I want possessive, I used double quotes so I could use the single quote or the apostrophe in the character string. So you can use single quotes and double quotes in your character string, but to enclose that character string, you have to use the opposite type of quotation. Look at sets and equals. The difference between those two is that an equal can only be used once, where a set can be reassigned later. This first one is called value name. I try to set that equal to 056, but you see on the left-hand side, the assembler has given me a multiple definition error, the M, because I had assigned value name earlier in the code, and it doesn't like that. It's a equals. Once you set something equal to something, it can't be changed. Set, on the other hand, you can change as many times as you want. So I have name. I set that equal to 011, and you can see on the left-hand side, it sets that equal to 011, and then I just reset it again to 011 hex, and it just resets it. It doesn't have a problem with that. The next little block of code here you can see is where my include ASCII definition opcode was. And then this is the file, just verbatim, of all of my ASCII definitions that I often use. So I use, for example, CRLF as carriage return line feed. So this is where I have set them to their ASCII value. And you can see back here, I didn't point it out, but when I was assigning when I was doing an ASCII string data byte, you can see I said hello world in quotes, and then I put in CRLF. Instead of having to put in the numeric value for those, it's just easier to read code if you've put them in as that value. And the reason this worked was because I had that ASCII definition included in this file. If I didn't have that include statement, that would throw up an error that it didn't know what a CRLF was. A very nice set of assembler directives are the if, then, else's. So for examples, we have if and a condition, and in this case, the condition is just built in, it's just 0. So that's going to be a false. In a if, then, else, it's either 0 or it's not 0. So this is going to evaluate as false. And you can see that the assembler just completely ignores everything between the if. Once it sees that condition is false, it ignores everything between the if and the end if. So it's just as if that didn't exist in the code. So it's completely ignored that. Anything I did there is gone. For example, how that can get us into trouble is I then tried to use the name oops, but I had defined oops up in the code that was then skipped by the if. And so that gives me an undefined label or an undefined name because oops was never assigned because it skipped that portion of the code. Let's do the same thing again, only this time we're going to use if, else, and endif. So we have if, I set the name, I then use equates to set oops2 and oops3, and then I just have a bunch of other things. I put in no ops. We have the else, and then we reset name and we reset oops2, and then another no op and an endif. The condition was 0, so it completely ignored the first part, and it assembled the second part. So in this case, even though there was the same name used, oops2 was used in both halves, that's okay because it just treated the first half as if it didn't exist. But we can see again that can get us into trouble because here I want to use the name oops3, but oops3 was never assigned because oops3 was in the first half, was in the if portion, but that wasn't assembled, and so oops3 doesn't exist. Labels can come and go depending on your conditional statement, and you need to make sure that if you use a label that it was actually assigned. Let's do it again with a condition. First, we're just going to set condition equal to 0, 0, 0. So when we use condition, it's going to be false, and that's what happens here. We see that if condition, it's going to interpret condition as 0, 0, 0, and you can see over here on the left-hand side, it showed us what it interpreted that as. So it's going to skip that, and it's going to do the else portion of the statement. The next one, we set condition to 0, 0, 1, and now we do the exact same thing, and on the left-hand side, it shows us that it evaluated that as 0, 0, 1, and so it did the F portion and skipped the else portion. Showed you earlier how you can use the program counter to check, for example, the length of a block of data. You can do things like have the program counter check for the length of code. Here I've set a name for the program counter called current PC, and it's at 010341. I then say, what's the difference between that and where the code started? That gives me the value 341. So there's 341 bytes that we've used here, 342 probably because it started at 0. And in my if statement, I say if the difference, which is the number of bytes of code, is greater than 377, then tell me that the code is too long for the page. In this case, that was false. As you can see on the left-hand side, it evaluated that as 0, 0, 0. And so it gave me the message that says code will fit. A little simpler way of doing it is to put the condition just on the same line rather than creating names or variables for that. And this is just a different way to achieve the same result. Last few things are that no matter how many errors you have on a line, the assembler will only flag the first one as an error. So here's a line that's got 3 errors. It has a label that begins with a 0. It has a mnemonic that doesn't exist. And it has a comment that doesn't begin with a semicolon. And in all of that, it just found the first error. The first error it set as a label, and then it didn't evaluate the rest of the. This becomes a problem when you think you fixed an error in a line. You reassemble and it still shows you an error. Well, it's possible that you had 2 errors in that line or multiple errors that were hidden simply because the assembler wasn't evaluating it. Finally, let's look at some expressions. Here we have standard unary addition. So 1, 1 we set equal to 0, 1, 0 octal plus 0, 0, 1 octal. You can see the value it set it to is 0, 1, 1. We have binary addition where we have set 0, 1, 0 plus 0, 0, 1 in binary. We can shift. In this case, we're going to take 0, 1, 0 in binary. We're going to shift it left by 1 position. And so that gives us 0, 0, 4. We then take that 4 and we shift it back to the right by 1 position, and we get our 2 back. We then take our 4 and we shift it right 2 positions, and it gives us a 1. So those are our additions and our left and right shifts. We can do Boolean expressions. If we take a 0FF hex, so all 1s, and we AND that with everything except for the least significant bit set, it's going to clear everything except for that least significant bit. And so you can see the value it gave us is a 0, 0, 1. We can OR. So let's take the 1, which was 001, and OR it with 0F0. So it's going to set all of the high nibble 1, and it's going to set the least significant bit to 1. So that's what it's done over there. We have our 361. Exclusive OR 0F0, and if we exclusive OR that with 0FF, it's just going to flip the bits. We can see that that has given us the 017. NOT is just a way to invert it. If we do a NOT on 0FF, it gives us 000. Finally, let's look at the high and low expressions, which we used before. If we take the high of 012,345, it gives us the 012. If we take the low of 012,345, it gives us the 345. Now we can look in the manual and it will tell us what all of the errors are. The little symbol, if it's a U for undefined, or L for a label, or M for multiple defined. The user manual for the assembler that we downloaded with the assembler gives us all of those errors. So that is it for this little series on assembly for the 8008. If you have any questions, let me know, and I appreciate you watching. Thank you. Bye-bye.